All right. Thank you, Chava. So it's my great pleasure to introduce our speaker this week, who's Gaurav Mahajan. He's a fourth-year PhD student at UCSD, where he works with Sanjay Dasgupta and Shachar Lovett. Before that, he has worked at Microsoft, and even before that, he did his degrees at IIT Delhi. He also worked at the Institute of Advanced Study and the Simons Institute that did a lot of cool work on reinforcement learning, more recently complexity theory, active learning, unsupervised learning, a bunch of cool stuff. And today he's going to be telling us about his latest work on these amazing class of MDPs. It's called Bilinear Classes, where you can learn efficiently and generalize efficiently. So with that, please welcome Gaurav. The stage is yours.
Great. Thanks for the introduction. Okay, so yeah, I'm Gaurav, and today I'll be talking about my paper, Bilinear Classes, and this is joint work with my awesome collaborators, Simon Du, Sham Kakade, Jason Lee, Shachar Lovett, Wang, and Ruosong Wang. So over the last few years, there's been a revival of interest in understanding generalization in RL, and today I'll give an overview of how we are thinking about generalization in RL and how it's related to generalization supervised learning. So why do I care about this problem? So over the last few years, there's been a lot of empirical success in RL. And if you play any of these games, especially Dota 2, it's a great game. But over the last few years, the AI has been like super awesome. And it has like significantly improved. But if you want to kind of become more ambitious and try to use these algorithms in your fields, we kind of like some of the questions in RL become super important. And one such question is, how do you deal with large state spaces? So over the last few years, there's been a growing theoretical work trying to come up with assumptions which let you deal with large state spaces. So in this work, we're trying to understand if these assumptions are really different and they lead to efficient RL for different reasons, or there's something really common about these assumptions which leads to efficient RL. So can we somehow unify these assumptions and look at them from in a clearer, like unified way? So I'm free to having some questions here, and if there are any questions, I'll be happy to take them. Some of the slides might be super dense in notation, and they might be pretty bad notations. So I'll be happy to clarify if there are any questions. Okay, so in this talk, I'll introduce natural sufficient conditions, which capture learnability in a large class of models. In the first part, I'll talk about what I mean by generalization reinforcement learning and how it's connected to generalization supervised learning, how generalization supervised learning doesn't trivially imply generalization reinforcement learning, and what are the issues there. And the second part, I'll introduce this unifying sufficient condition and show how various model assumptions that people have been using before imply this sufficient condition. And then I'll give a simple algorithm which works for this sufficient condition and a short proof why everything works. Okay, so let me introduce the framework for RL. It's a Markov decision process. In Markov decision process, you have an agent and an environment. So at time t, agent is in some state st. It chooses to take action at. Because of that, environment transitions to state st plus 1 and see a reward rt plus 1. And this goes on. And the way to formalize that is to say that the agent is trying to learn a policy, which policy is just a map from state to actions. For example, in Mario, a policy could be that you always go right. So you can execute a policy to obtain a h length trajectory. Basically, if you start from state S0, policy tells you what action to take. That would be A0. Because of that, you receive reward R0 and transition state S1. And this goes on for h length, which we call the horizon of the problem. For example, in chess, h could be as big as 80. In game of Go, it could be 150. And complex games like Dota 2, it could be as big as 20,000. And the goal is to learn a policy pi, which maximizes expected sum of reward. So why is this problem hard? There are issues like environment being unknown, so we don't know how to explore in some sense. Also, there's issues of credit assignment. What action led to bad rewards? Was it the action you just took or something that you took in the past? But one of the main issues is that these state spaces are really large. So they're in really high dimensional spaces, so you have curse of dimensionality. So you really need to somehow generalize from bad state action pairs to what are other bad state action pairs. And from good state action pairs, you want to generalize what are other good state action pairs. But we know how to deal with cursor dimensionality in supervised learning. So in the first part, I'll go over what I mean by generalization supervised learning, where we deal with this kind of issues. And then I'll introduce what I mean by generalization supervised in reinforcement learning and what are the connections there. Okay, so we know how to do generalization in IID supervised learning setting. Here to get epsilon close to best-in-class happiness class, we need number of samples which are only logarithmic in size of class and polynomial in 1 over epsilon. And if we can extend this to infinite happiness classes, where we just replace the size of class with some kind of complexity measure like VC dimension. And for example, for linear regression in D dimensions, we only need O of D over epsilon square samples. And the main idea in supervised learning is uniform convergence or data reuse. Basically, if you have a training set, you can use that to simultaneously evaluate loss of all hypotheses. This might not be computationally efficient, but statistically, this gives us a way to solve generalization problems in supervised learning. And in fact, for packed learning, you can show that uniform convergence is equivalent to learnability. So why doesn't this work for RL? Well, the first issue is that we don't have an IID data set to do generalizability in RL. But another issue is that maybe we can somehow use a single data set to learn the value of all policies in our policy class. So we'll see why that doesn't work, but let's talk about RL without any generalization. So we have a tabular MDP, and let's assume it has small number of states and actions, and I want to find the epsilon best policy here. Using number of samples, which are polynomial in number of states or action and horizon, can I do that? Even here, there are some issues. Basically, if you end up, if you end up in this state, it's unclear whether the action you just took was to be faultier or something that you took in the past and you went in the wrong direction. Another issue is that you kind of have to explore this tabular setting to find where the good or the bad states are. So you have to find out where this green thing is, where this red thing is. But in spite of all these problems, Kearns and Singh in '98 showed that if you want to find the epsilon best policy, you only need number of samples which are polynomial in number of states and actions and horizon. And the main idea they used here is dynamic programming and optimism. You can use dynamic programming to deal with the credit assignment problem. Basically, you can assign credit to all these actions. And to explore well, you can use optimism. Basically, all the states that you have not explored before, you add bonuses for them, so you explore them. So let's add generalization to this problem. Now, we're talking about games like Dota 2, where state spaces are pretty large. So we really don't want these dependence on number of states. How can we find an epsilon best policy with no state dependence. So then the question is, we need to really generalize here. Can we somehow reuse data to estimate the value of all policies in a policy class? And something very simple works here. You can basically act randomly for length h episodes and use important sampling to evaluate each hypothesis in your class. This has pretty bad variance, so you pay for that. But other than that, Kearns, Mansoor, and NG showed that you can find epsilon best policy in class by just acting randomly over the tree. And this gives you an optimal policy using the number of samples which are logarithmic in size of class over epsilon squared. But you pay this exponential in h, or horizon dependency. And the question is, can we somehow escape this exponential in h dependence? And it's no, because if you just look at a binary tree and you have sparse reward in one of the leaves, you really need to explore the whole tree before you can find this special node. So there's no way without in this setting that you can escape this a to the h lower bound. Okay, so can we somehow escape this lower bound by making more assumptions? Yes, and there are a lot of them. You can assume that the MDP is linear Bellman complete. There's linear MDPs, Flambe, linear mixture models, block MDPs, vector MDPs. And all these works have their own algorithms and own analysis, how you can get efficient RL, basically no dependence on number of states or actions, and some dependence on some kind of complexity measure that they define. Okay, so that's the I think this is the sorry. Thanks. So that's the story up till now. If we don't assume anything about our MDPs, then you really need to pay this a to the h dependence. And if you're okay with making assumptions, then there are lots of assumptions that you can make. And lots of different, all these things are really different assumptions. They make different analysis and different algorithms and different proofs. So can we somehow unify them? Are they really different in the sense that the only unifying thing about them is that they lead to efficient RL? Or there's actually technical similarities here, that you can have a single technical argument which kind of proves that all of these settings would have efficient RL. And to kind of make progress there, and to motivate what I call these common sufficient conditions, let's look at a simple case of linear bandits. Linear bandits are basically our problem where the horizon is just one. And the structural properties that we have in linear bandits is kind of going to be really essential and somewhat sufficient for us to see that all the other models basically just need this technical technique to make progress and show that they will have efficient RL. So what is linear bandits? Linear bandits is a one-step RL problem. So you have a single state S0 and large set of actions. So basically, if you want to generalize, you need to assume something more. And the thing people assume is that the reward is linear. So there exists an unknown vector W star in D dimensions, and a known feature map phi, which maps each action to a D-dimensional vector, says that expected reward when you take an action A is inner product of these two vectors. And it's a classical result that you can actually get polynomial sample complexity here. And the way you do that is you actually start using a linear value-based hypothesis class. So what do I mean by that? So there is a set of bounded linear vectors in d dimensions, which we call our hypothesis class. And for each of these vectors, I think there's a question in Java. Oh, later on. Okay. And for all these hypothesis class, you can define Q value as basically the inner product of the feature with this particular vector. And you can define V and greedy policy greedily. So you can define V to be the max of these Q values over actions, and policy to be the action which gives you the maximum Q. So each hypothesis leads to its own Q, V, and pi functions. And we can see a really important structure property emerge here, which we call bilinear regret. So for every hypothesis in this class, if you look at the on-policy difference between the claimed reward, which is just this expected Q value, and the true reward, which is the expected reward, it satisfies a bilinear form. So basically, you can write the Q value for hypothesis W as just the inner product. R is also an expectation this inner product W star times phi. So you can just write it like this. And this basically, if you square both sides, this is basically some way of measuring distance between W and W star in some kind of scale norm. So if this norm was Euclidean, then you can basically, if you can estimate this distance for all W, where maybe this thing is just a covariance for this vector. Then if you can estimate this thing for all hypothesis W dash, then you will be done statistically, and then it would just be a computational problem. And that's what we get in this problem. Essentially, there is a loss function such that for any hypothesis W dash, you can estimate this norm efficiently. So you just get data using some other policy, and then you can use that to estimate this norm for all other W dash.
Was a question.
Yeah.
Whether is it obvious that this inner product is a norm?
So okay, so I think there's an echo. Okay, good, thanks. So it's a norm if, okay, it's L2, it's a norm. But if, so if you look at these things, if you look at the squared of, it will be, so the way I'm defining the sigma is basically so it's a rank 1 matrix, it's PSD, so it will create a norm. So as long as the inner thing is PSD, it will lead to a norm. You can check all the properties will be satisfied. And basically, there can be some bad things which can happen because, what if these are all zero vectors? Then you won't probably satisfy this identity thing where if you have two different vectors, they could lead to same zero. But you can add, say, lambda I, and you'll be very close to, so you can add some kind of small identity matrix, which will lead to all eigenvalues being larger than 0. And that's exactly, in some sense, what we do. But I'll go over this in more detail later on. Okay, so linear bandits satisfy this these properties. And what I conjecture is that these properties are enough to solve all the previous known results. And all previous known results somehow have this kind of structure property. And so to generalize that, let me just write it more cleanly. This is what we call bilinear classes. To define this, we'll need a hypothesis class. And for every hypothesis in our class, I'll define a corresponding Q function, V function, and pi f. And this hypothesis class could be parameterizing a model-based class, or it could be parameterizing a value-based class. So it could be parameterizing these Q and V values directly, or it could be actually parameterizing some dynamics, and we could be inferring Q and V values and pi's from there. And once you have a hypothesis class, we say a hypothesis class and a loss function pair is a bilinear class if there exist two functions, W and phi, which map these hypothesis class to d-dimensional vectors. So there's two properties hold. The first one is bilinear grad, basically the on-policy difference between claimed reward, which is Q minus F, Q minus V here, and true reward, which is just a reward. So this on-policy difference, of which people also call Bellman error, is upper bounded by this bilinear form. And if you kind of square both sides, then you see this is some kind of norm. The second property we need, actually, before I go on, a couple of remarks about this thing. If you square both sides, norm, also both the sides are 0 if you choose the optimal f star. So if the optimal policy is in this class, then this left-hand side would be 0 too. Okay. And the second thing we need is data reuse, which basically says I can estimate this bilinear form for any other hypothesis. So I just replaced that f with g. So you can estimate this kind of norm efficiently. So there exists a loss function which lets you estimate this. And as foreshadowing, like this L is basically where the supervised learning problem would be, and we'll pay for the generalization error of this L over the hypothesis class. So the only thing we really need is for this loss function for each hypothesis to concentrate nicely. So I'll give a few minutes for people to go over these things because it's somewhat dense.
So regarding this value function that you have in there, this v of f, is that supposed to be like an estimate of the optimal value function?
So
the definition fully yet.
Yeah, no, that's great. So this is for each hypothesis in a class. For every hypothesis, I'll have Q of f, V of f, and pi of f. These could be arbitrary functions. This could be any functions they could be. The only thing I require is that this V of f is, okay, I should probably write it, is basically so this is the only consistency I require. So however you define Q of f, I want V of f to satisfy this equation. Similarly, I want pi of f to be max. Okay, and I
see. So basically, V of f is like already fully determined by Q of f.
Right.
So it's like
or
not a separate,
the other way around.
Separate function class.
I mean, you can define V of f and then.
Q of f sure. Yeah, with one step. Okay.
Yeah. So in some cases, both of these things would be, so Q of f would also be determined by, so for example, in some cases, I'll be parameterizing the transition function. And both, all these Q, V, and pi will be determined by just determining the dynamics.
I see. But that sounds like a very important condition that you assume these to be consistent.
So yeah, it affects computational complexity, yes.
Right.
For in some cases where you have like these function approximation things like Q star linear, V star linear, imposing these conditions is statistically easy if you have all the features mapped, but computationally could be very, very hard. Okay.
Right, and there's a question in the chat by Kishan. He was asking whether there's any conditions on the loss functions. LF.
Yeah. So so the only condition you need for these loss functions, okay, you can make as many assumptions you want, but the only one thing I'll need is just bounded. So the way you should look at this loss function is that eventually the generalization problem in RL would be turned into a generalization problem over these loss functions. This will be a supervised learning problem where you have these loss functions, these hypotheses, they will define their own loss functions. Do these loss functions generalize? So if they're bounded, they will generalize, but they can generalize for other reasons too. So yeah. So the thing I'll show, the theorem I'll show will use that these are bounded. And for all the examples I'll look at today, this will be bounded, basically bounded by horizon. Okay. Okay, so our first theorem, there's another question.
Yeah, I think those questions are going to be answered here.
Okay. The first main theorem is that all these models that I was talking about, they're actually bilinear classes for some bounded loss function. And so, for example, linear Bellman complete, linear Mdps, which is a special case of linear Bellman complete, generalized linear Bellman completion, Flambe, all these models, they're all bilinear classes for some bounded loss function. There are two exceptions to this thing. One is deterministic linear Q star and Q star state action aggregation. And basically both these, all the algorithms for these settings, they use some kind of no amplification, error amplification techniques. So basically you can go from one level to another level or across the things. You don't amplify the error. So these are kind of techniques that we don't cover in our setting. But other than that, we cover everything. And essentially, we also generalize Bellman rank and witness rank, which were the other two previously known generalizations. And they're quite cool. And actually very similar to how we define things. And it also leads to new models. I'll talk about a few in the next few slides. Okay. So what's the algorithm? This algorithm takes in few inputs. First input is number of iterations. You can think of number of iterations as around number of dimensions, so D. So if you're in D dimensions, then you would set this number of iterations to be around D. Loss function is basically defined per problem. So if you are looking at linear MDPs, you would have some loss function. If you're looking at Bellman complete, it will be another loss function. We'll set batch size later on in the theorem. This will be related to generalization of L. And then we would have confidence radius, which is also related to generalization. Okay, so the way we'll do this algorithm, we'll have this discrepancy function. This is basically for each hypothesis to assign a real number. And in the beginning, I'll start the algorithm by setting this thing to be 0. And over the iterations, I'm going to build this discrepancy function. So I'll do this algorithm for t iterations. So at every step, I'll find an optimistic hypothesis ft, so which is just maximizing v in a class of functions which satisfy this constraint, where I'm saying I want the discrepancy function to be small. And I'll define how R is, but like for now, just consider R to be some constant. And once I find this optimistic hypothesis, I'll use that to sample M trajectories and create a data set of size M times horizon. And in this data set, I'll have the reward, the state action, and the next state. And using this data set, I'll build my discrepancy function. I'll basically want my discrepancy function to have small loss over this data set. And then I'll just repeat. So at each step, I'll build my discrepancy function. So it will make the set of functions which satisfy this constraint smaller. I'll find the best function, optimistically best function in this class. I'll sample some trajectories from it. I'll build my discrepancy function and so on. And I'll only do this d times. So if you're running d dimensions, I'll only do it d log 1 over f, so something like that times. And at the end, I'll just return the best policy I've seen up till now. Oh, well, sorry, I'll stay here if there are any questions, and then I'll prove.
Well, I think it's all pretty clear.
Okay.
Maybe my question is, why is this called bilin UCB? Is there anything bilinear happening in this algorithm?
Well, it's so bilinear is the name of the class in somewhere in UCB. Well, I mean, I'm open to new names, but I don't really.
Yeah, I'm just saying that it doesn't really evoke anything specific regarding this algorithm.
Okay.
It's a very general algorithm.
Yeah. Yeah. Okay. Okay. So why? So our next theorem is that this algorithm works. So if you have hypothesis loss pair, which is a bilinear class, and the features in the definition are in D dimension, and the loss is bounded, and the class is realizable, so Q star is in the class, then you can set M, you can set the other parameters such that using only d square over epsilon squared trajectories, poly in horizon, log size of class, log 1 over delta, you can find epsilon optimal policy with high probability. And I'll go over the proof in next few slides. Proof is super simple. It's just 2 pages, 2 slides, and uses elliptical potential lemma. And you can extend this proof to infinite dimensional problems where you just have this extra max information gain parameter. Okay, so let me go over the proof. So the proof basically follows from this lemma. So I'll just prove this lemma. It says that if I run my algorithm for d iterations, then there will exist an iteration where the suboptimality will be pretty small. And this is basically upper bounded by generalization of L. So L is this class of, so if I write loss function for each hypothesis, it's just basically a class of loss functions. So if this one is just Hofting bound. So I'm saying if it's bounded by H, I can basically Hofting bound it. And I'm saying I'll pay extra H root D factor over on top of it for generalization in RL. Okay, so I'll prove this in 2 parts actually. So first I'll prove bilinear regret lemma. This is pretty standard, but I'll go over the proof anyways. So this basically uses bilinear regret assumption that we had before and optimism. So what this is saying is that you can upper bound the suboptimality by the sum of these bilinear terms. So you can sum over the horizons over these bilinear terms, and that will upper bound suboptimality. this is for all iterations. So the first step basically follows from optimism, because I chose FT to be the optimistic one, and I don't remove the optimal policy ever from the class. VFT will be just bigger than V star. And then I'm just doing a telescopic sum. I'm adding Q, FT, SH, AH, and subtracting it from each sum. So I can write it like this. And then this is basically the bilinear gradient assumption that each of these terms is upper bounded by a bilinear form. So basically with this thing, in somewhat sense, we have connected the suboptimality with how big these bilinear terms are. Yes, it's an equality. Good point. Yeah, so you can upper bound the suboptimality by these like somewhat norm terms. So as if you're close to W star in this norm, then you'll actually have small suboptimality. So you'll be pretty optimal. Okay. Okay, so now with that proof done, so what does this mean? It means that I'm just looking for iteration T where the sum is small, right? And for that, I'll actually show that there exists an iteration where each of these norms are small. And the way I'm defining these norms, I'm defining sigma 0 as basically lambda I. And for each time t, I'm just adding all these covariance matrices in there. So basically, you can ignore H for now if you're just reading it. And so this is, so I'm doing it for each horizon. I'm just adding all these new directions into my covariance matrix. And basically, the way this, yeah, I don't want to go forward, but like, yeah. So you can somehow write this sum of bilinear terms as basically a sum of these product of these norms. And the only thing you need to show is that both these norms are small for some iteration t. And why would that be true? The first term is small. This term is small just because our optimization constraint. This is exactly our optimization constraint. So the question is like, how small can we make R? And so the first thing is, this thing will be, if I just look at the distributional version of this, that should be 0 for F star. So the only thing slack I need is basically the generalization error. And because I'm running this for D iterations, so I only need to, so I'm only adding these D terms of small generalization error. So the whole thing would have root D generalization error. So I can make R basically this small. So I can make the first term super small. And essentially, if I choose M large, I can make this as small as I want. And the second term is small because of elliptical potential. Basically, the second term is saying how many new directions you can find in some sense. So is that it's really far away from all the previous directions. And elliptical potential lemma says that if you're in D tries, you'll find something where this is O of 1. And I'll give a proof of this, both of these things, and a geometric intuition for why you only need D of these. And this is
so I guess,
yeah.
So maybe one question is that in the middle, you say that from the optimization constraint, this inequality follows, but actually what you're controlling is the loss, right? And not directly this norm.
Yeah, so it implies, so loss implies this thing, right?
Right, because the loss is a lower bound than this.
Yeah, so
that is an
that's the
important
data reuse assumption, yeah.
part.
Sorry, I should make clear about that, yeah.
Yes, all right.
Yes, yeah.
Good. And I guess that order 1 at the bottom, that's more like an order log t, no?
So yes, so one of them would be lower than log t, but then it's divided by t, and t is like d. So you can make it like very small. I mean, this actually grows, like decreases exponentially. So we have like in our paper, we have exact relation between how it grows, and it grows like exponentially small. So it's pretty fast actually.
Right, yeah, actually the sum is convergent.
Yes, exactly, yes.
Yeah, right, okay, got it.
And there is a nice geometric view of looking at it too. So, okay, so the proof for the two potential lemma. So what's this lemma? It says that if you have a sequence of vectors in some Hilbert space, say, let's look at like d dimensions. Then if you look at these matrices, where I'm kind of growing these matrices by adding these rank 1 matrices, there will exist one vector for which this log norm is going to be small, or it's going to be upper bounded by this term. And the reason this is true is basically, this is exactly matrix determinant lemma. If you add a rank 1 matrix, you don't increase the determinant by a lot. And a geometric view of looking at this problem, or it's similar to a problem in the sense that, say I have a set of points, S. So a lot of points. Yes. And I want to cover them with a convex hull of some kind. So I want to find a subset C of S such that if I blow up the convex hull of C by, say, a factor of D, then it covers the whole set S. One iterative way of building C is that you just pick any point from the set S. If it's outside of the current C's D convex hull, you add it to C, and then you build this new D convex hull, find another point which is outside, add it in there. You kind of do this process. You cannot do this process more than D times in D-dimensional space, because it blows the volume of this set by a constant factor, and you can blow the volume of a set by more than D times. So this process is very similar to how elliptical potential kind of says that after D times, you cannot grow, because determinant is basically volume in D dimensions. Okay, so with that proof done, and if there are no questions about the proof, rest of the slides are basically about how different various model assumptions imply bilinear regret and data reuse properties. So it's going to be very small proofs, basically a slide for each of them. Okay, so what is linear Bellman complete? So linear Bellman complete makes two assumptions. The first one is that Q star is linear. And this will be assumption we'll use in most of these cases. It's kind of very natural. So you have an unknown vector W star and known features in D dimensions. So the Q star is the inner product. Another assumption it makes is called completeness. Basically, if you have this value-based hypothesis class, you pick any hypothesis, look at its one-step Bellman projection, that should also be linear. And then et al. In 2020 showed that polynomial sample complexity is possible in this setting. So let's see how it satisfies bilinear regret. So because Q is linear, for our class, we can write Q as this inner product. And because of completeness, R plus V, an expected value of it, is also expected value of this inner product. So we can write like that. And then this is the first step. Next step is straightforward. Here, I'm just using the fact that if you have optimal policy in your class, then W star and TW star should just be same under this expected value. So this is basically, this term is basically 0. And how can we estimate this norm for other hypotheses? There exists a loss function which lets you estimate this W dash term. And that loss function is basically Q of W dash minus R minus V W dash. And the proof is basically how we are doing this. So for any other hypothesis, you can directly, just by sampling one data set from pi, you can estimate this loss for all other W dash. And so this gives you statistical efficiency. Okay. The next one I'll go over is linear Q star. So I already explained linear Q star. It's basically saying there exists a d-dimensional vector and features phi, so that Q star is linear. And so this is like pretty old, and also Shannon used or hinted on this Q star assumption that Q is linear or close to linear for chess. And it's a pretty cool paper of why he thinks it's linear. And then a lot of people have worked on this using this assumption. This is also used in TD Gammon and Atari. There's some function approximation for Q. So I mean, it would be a pretty natural thing to solve this if we can say linear Q star is enough for efficient RL. But recently, Wise et al. Showed that if you have a deterministic, there exists a deterministic MDP and features which satisfy this assumption, so that you need exponentially many samples to find the optimal policy, even up to constant additive error. So you really cannot solve linear Q star efficiently, even statistically. But say that you make another assumption, say that V star, the best, so distance between best action and second best action is always lower bounded by something. Then there exist algorithms for deterministic MDPs and even stochastic rewards. But Wang et al. Showed that there exist stochastic MDPs, where even if you have these two assumptions, then you cannot find optimal policy using polynomial many samples. So all is lost here. But maybe we can assume something more. So what happens if we assume the linear Q star, we have Q star is linear and V star is linear? Then, so basically what I mean is like there exists a single W star, but there are known features phi and psi, which map state action to d-dimensional space and states to d-dimensional space, so that both are linear in these features. Then can we get polynomial semi-complexity? And we can show that actually this is also a bilinear class. So we'll use here the value-based have this class. So we'll use linear vectors, define Q and V correspondingly for those vectors, and define the optimal policy based on Q. And then this satisfies bilinear regret. Basically, you can replace Q by its inner product, V with its corresponding inner product, and R is basically Q star minus V star, so it's also linear. So you can write it as W star. So R is basically W star in a product with these vector. The question is, can W star be different? Yes, it can be different. And that would imply you can just club them together and make a same W star.
So wait,
yeah.
I will type my question.
Sorry about that. Okay, so I'll keep going on and then wait for your question. Okay, cool. And you can estimate this thing. If it's just linear, you can just use L to be exactly the same thing as before as the Bellman error, and you'll be able to estimate this loss for any other hypothesis. Maybe this is what Trevor is going to ask. So you also need, yes. No, wait, so sorry, let me look at the question. Here we assume that V max, yes. So the assumption we make here, it's probably not written, is that you remove everything where this is not true. So you can ensure this property is true for all hypotheses without even looking at any samples. By just looking at the vectors. So, I mean, statistically, you can choose any phi and psi, and you can just remove all hypotheses which don't satisfy this. Yeah, you need to see all features, or you can use something like some ideas from TensorPlan to clean it up. Actually, there are easier ways to enforce this condition. You actually don't need it for all. You don't need to for all phis. You can find nicer phis and just d of them, and you can pose it over there, and it will imply everywhere else. You can add it in the constraint. So this is something new that we have been thinking about, but it's very easily possible. Okay. So next thing is a model-based class. So here we'll be parameterizing the dynamics. So we have linear dynamics and rewards. So there exist unknown vector W star and known features phi and psi, such that both dynamics and expected reward is linear. And these vectors W star could be different for these things, and you can club them together. And Modi et al. In 2020 and Ayub et al. 2020 showed that polynomial sample complexity is possible here. Okay, so what's the hypothesis class we'll use here? Again, do all bounded vectors in dimension. And for each hypothesis, you define the dynamics as basically the inner product. And you define Q, V, and pi as basically the optimal functions. So this also satisfies bilinear regret. Basically, maybe I should spell things more here, but you can write, because Q was the corresponding optimal function for this dynamic PW, you can write Q as W times this expected value. And this expected value is exactly with respect to W star. Maybe I should have written more clearly, but okay. And you can estimate this thing for all hypotheses. Looks very complicated, but you can use this function to estimate this loss for all the hypotheses. Another thing is feature selection for low rank MDPs. This is basically linear MDPs, but you also have to find the features. So even the features are unknown here. And the only concession given to you is that these features lie in some small class. So you're okay with even having some dependence on the size of the class, size of this set of features. And Agrawal et al. Showed that polynomial sample complexity is possible here. So the way to see why this satisfies bilinear regret is, okay, so we'll look at this model-based class where each hypothesis is this pair. And we'll define the corresponding dynamics as just their inner product. And we'll define Q, V, and pi as basically the greedy Q, V, and pi. So this satisfies bilinear regret because, and we are lucky that I spelled it out nicely here. You can write, so this expectation here is over SH and AH pair, but here I'm just opening up the measure here, and I'm writing the probability of seeing state S after you have seen state SH minus 1 and action AH minus 1. This is basically probability, true probability. I'm just integrating over this. So this is basically expectation of this thing. And now I'm just writing, so this is basically just rewriting the above thing as an inner product. And so we can estimate this whole thing. Looks complicated, but it's not actually. You can just, you have to use a uniform policy now for each level. It's still efficient. And you can estimate this thing. And that helps you estimate double dash. So the only place where this thing differs is that now we are using some kind of uniform policy, but it's still efficient. And that's it. So we're showing that generalization theory in RL is possible. And basically, all the techniques that we used are from linear bandit. So just using techniques from linear bandit, you can show that there are lots of RL models which lead to efficient sample complexity. We cover a lot of known cases, give some new cases where efficient RL is possible. We show a simple algorithm which works with this condition and a simple proof. So there are lots of open questions though. And some of the things that I'm really excited about are, what's the computational statistical trade-off here? Can you create computationally efficient algorithms for all these settings? We only know for linear MDPs how to do this efficiently. Another question is, what's the so in pack learning, agnostic learning and realizable learning are equivalent. They're direct arguments, but basically you can say that BC dimension is finite, so both work. But we don't know any such thing for RL. Basically, we have some examples where realizably things are possible, and agnostically we don't know how to do things statistically efficiently. But maybe there's something deeper going on here. So those are the questions I'm interested in. And thanks again to my collaborators. And I can take any questions if there are.
All right, thank you. That's very nice. So I suppose there were a bunch of questions during the talk. Like, I don't know if all of those have been answered.
I can go with them. Are they all in the chat, right? Or...
Yeah, so there was some lengthy discussion there that I didn't truly follow between Chava and Akshay and all these folks. Do you feel that this is concluded? Akshay, for example? I see that Chava is just lost.
Oh, yes. So he's talking about, I think, linear Q star V star. So in this algorithm, you need to see all features before, but well, we didn't know the Chava's tensor plan algorithm before, but after looking at his algorithm, there's another way you can solve linear Q star V star where you don't have to see all the features before. You can add the features that you have seen up till now in some nice way into the optimization constraint, and that will work. Basically, okay, every time you find a V which is not equal to max QA, all right, so you can show that it actually implies that the product of A V minus Q is not 0, which is linear. So you can only find D to the A such things. I don't know if that makes any sense, but adding those constraints is enough. So you don't actually need to look at all pairs. But this is all in hindsight and after looking at Chava's paper. Other questions?
So actually, I have a question regarding the algorithm itself. So
yeah, let me go back.
So like the whole algorithm specification relies on these loss functions that you have specified, well, basically as just like a Bellman error pretty much for most of these applications. But then in the algorithm itself, you're putting a constraint on the squared losses.
Yeah.
And I'm just trying to understand if this corresponds to like any common algorithm that would rely on like minimizing the squared Bellman residual, or this is something different?
So if you just use, so I mean, there are a lot of places where I don't use Bellman error, right? So, but the cases where I do use Bellman error, I mean, this is very close to, okay, well, it differs in some ways. So, okay, so, so this loss, the way I'm collecting this data set, I'm sometimes using PyFT, but in some cases I can use other estimation policies too. So this is a simplified version of what's in the paper, but you can roll with PyFT, and just for one step, you can use some other policy, say like maybe, so you roll in with PyFT, and then for one step, you use some estimation policy. So for example, in, I think the last example I showed, that was uniform. So you roll in PyFT and then do uniform. So if you use like this G, so some, like if you talk about bilinear, Bellman rank, the algorithm Bellman rank, it's very similar to that one. I mean, technically it's similar, they do slightly different things, right? But yeah, it's very similar. But they use a uniform policy all the time. So they have this dependent number of actions. So if you do uniform, then you have to pay like in statistical thing, number of action thing. So which could be pretty bad for some of these settings. And also sometimes uniform is really not the right thing. Like sometimes you have to actually look at PyF. So for example, for Bellman complete, I think you have to look at PyF. Otherwise, just doesn't make things.
Yeah, I guess I'm just really wondering whether or not you run into like a double sampling issue at some point. I mean,
no.
maybe I'm just not understanding the details quite enough.
So double sampling issue would arrive when you're not looking at expected value, but you're looking at, oh, I want for a single state 2 samples, right?
Yeah.
So that's the whole point. We don't want to do that. We are just looking at the expected value of this loss. And as long as you can compute this loss,
Yeah.
expected value under this distribution is stable.
Yeah, right.
So I think we are getting rid of this double sampling issue because of these assumptions. If we didn't have assumptions, then we would hit that double sampling issue.
Yeah, right. That's because your loss is, I mean, that's their property, that their expectation.
I mean, that's we require that you don't have to double sample. And I guess what we're showing is like all the other things basically had this property that you didn't need to double sample.
So Kishan had a question about offline RL. I guess one way to ask that question is, well, can you do like offline RL in general in these bilinear classes as well?
So how is offline RL defined? Like,
well, I guess maybe he can unmute himself and ask him.
Okay.
Kishan, are you here?
I can maybe assume if I mean, offline seems like you only have some fixed data set that you're trying to work on, right? And I actually don't know. I haven't thought about this problem.
Yeah, we would need an offline RL expert to chime in on that.
Yeah. Oh, he said he's traveling with a lot of background noise. Okay. He was referring to Ruosong's work. Yeah, I haven't followed offline RL. But I'm sure Ruosong would definitely know a lot more about it. If he's here, he might be able to answer.
Right, and then when you like listed all these settings that that these bilinear class captures, and you said that this was related to Bellman rank and witness rank. So are there any examples of these that are actually not captured by these previous notions?
Yeah, so factored MDP is not captured by Bellman rank, but it's captured by witness rank. Linear Bellman complete is not captured by any of them. Linear MDPs is, because special case, but still it's captured. So generalized linear Bellman complete will also not be captured by any of them. Flambe, I don't think Flambe is captured by witness rank or Bellman rank. And then I think everything else is captured. I'm not sure about KNRs. Yeah, I don't think those will be captured by. Wouldn't that might be captured by witness rank actually? Maybe not. But I'm pretty sure Bellman complete is not captured by any of them.
I see.
Okay,
so Bo had a question.
Yeah.
Which is very much related.
He's saying low rank MDPs without known features. I was wondering, is the bilin use? Oh, okay, that's a right. So he's talking about Flambe, I think, right? You can apply bilin UCB. Yeah. So why do you think it won't be applicable? So let me go there, actually. Right, this one, right? Okay, so yeah, I mean, the algorithm is different for Flambe, but you can apply this algorithm for the Flambe setting. So basically, because it satisfies all the assumptions, you can just run it. You don't even need to know any of these feature vectors in the algorithm. Just randomly choose and run the algorithm, and then it fails. It's basically the same algorithm would definitely work. Yeah. But this is different than Flambe algorithm, yes. So in the algorithm, the only thing we require is that we can estimate this loss. Oh, maybe I understand what you mean. You're saying, I think you're right. Okay, hold on. Let me go back to the. Yes. So this step has to change. So instead of using PyFT to do everything, you need to go to each level using PyFT and then use uniform.
Yeah, I think my question is, how can you maintain the exploration in the feature space?
This will explore in feature space too, because when I'm doing this exploration here, I'm basically saying find me both phi and psi, so both the sides which give the maximum V.
Okay, I get your point now. It seems like you need to, but
sorry, yeah. So the VF, the weights, so the weight F is defined. Okay, so let me write the assumption again. So it's right. This is we are saying this is. I'm just going to use different notation. Right. So this is my assumption, and I'm going to use both of them for my class. So I'm going to. So my F is basically a pair of phi and psi. So I think in usual notation, it's using both like vector. It includes the vector you're going to use, but also features.
Okay, got your point now.
Yeah. So it's going to explore both of these things together.
Yeah. Okay, I see. But it seems like it's a little bit conceptual because we don't know how to attractively get the phi here.
Yeah. So your sample complexity will depend on log size class of phi, right?
Definitely.
Yeah. So
that's a good point.
Yeah.
Thanks.
Right. Yeah.
So risking the echo. So in this case, if you had some continuously parameterized feature maps, would you get some result with some covering numbers?
Yeah. I think as long as you can guarantee that the true thing also is in your cover, I guess. But yeah,
It would be the same assumption, except that now you don't have a finite set, but you have a continuous set.
Yeah, I think it should just work.
And what's the so you're covering with respect to what metric?
So you can just do it in L2. I mean, these are just vectors in some dimension, right? Oh, I see. For features. Oh, interesting. Yeah. Oh, that's a good point. I haven't thought about that.
I feel that the dimension of the feature space is gonna
It's
go up differently depending on what you choose.
yeah.
Huh?
I guess it depends on how you're representing your feature functions and how do you define the cover there, right? So yeah, that's a good point.
Okay.
Flambe, I haven't read like Flambe in a lot of detail, like the original paper where they kind of deal with this. So I think maybe if Akshay still here, he might be able to answer this actually, because they might have talked about it, right?
He just left a couple minutes ago, I think. At least I've seen him gone, unless he came back. Yeah, maybe we can stop the recording and we can ask more juicy questions. Thank you.